So it is basically in AIML we are using for the purpose of cleaning the data and then transforming that data and reduction the data set. So you have a certain amount of data with you. That data may contain some noisy data, some missing data values or duplicate data within it that we have to remove before taking that data for the model uh, creation. Then after all the removal and cleaning, we have to transform that data into discretization, attribute selection, and feature scaling, which we will see in the next slide. Then after that, we will be looking at the reduction of the data by aggregation, feature subset selection, and dimensionality reduction. Then from that, we have to take the features, particular feature we have to select. Then based on that, we will be using that for supervised, unsupervised reinforcement or deep learning. And then we have to analyze the how the model has learned. So after that, we have to analyze, and after analyzing, we will get our model after uh, uh, making it with uh, proper model learning and removal of the unwanted data. Then we have to analyze the whole model. So just I have explained about the data cleaning, so you can see here. I will share. So this is the main data pre-processing steps or techniques, you can say. So this in detail we will see. So what's the data cleaning I have explained to you. So some noisy values we have in our data, then some missing values, and then some duplicate data. So all these we have to remove and we have to clean our data before using it. Then here just one example you can see I have used. So here you can see in the table that here these are the attributes. Attributes means the different types of your characteristics you can see, like a red, and having some values 0.25, 0.98, 1.02, like that, some values. So these all will come in the attributes. And then we are classifying all these according to the data we have, according to the value and color into classes like positive and negative. So here the value is 2.05 we are having, but color is not available. And here we are writing is as negative. And here it is having some different value other than this numeric value. And we have the color green. So we are writing just positive. So this data we are having some noise within it. This we have to remove. And here you can see missing data in our data set. So it is continuously some data is there, but here suddenly the age data is missing. Then cabin data is also missing. Some missing data values are there. That also have to remove. Then some duplicate data is having in our data set. Here you can see ID Setosa and ID Setosa are the duplicate data written here for the two IDs 34 and 37. So this kind of duplicate data also we have to remove. That comes the data cleaning part. Now moving on to the data transformation. So here three techniques we are using: discretization, attribute selection, and feature scaling. So in discretization, we have to replace the raw values of numeric attribute by interval levels or conceptual level, which we will see in the next part. Just we are putting all the raw data values into certain interval levels, and we are categorizing that data into different levels, like from uh, 0 to 1, 1 to 5, like that. We are just putting them into one particular level. Then we are selecting the attributes from the given set of attributes, and then feature scaling, and there we are scaling the data values into specified range from -1 to 1 or 0 to 1. There are also min-max normalization and z-score standardization. So these two methods are there in the feature scaling. This is the formula you can see here. This I will show you with an example so that you can have the better idea. And z-score standardization also we will see with an example what are these two things. Just a minute, I am sharing you can see. Hope you are able to see it. Min-max normalization transformation and z-score standardization, what I have told you now. So what is it? Min-max normalization transformation. So it scale values of a variable to a new range between 0 and 1 or another specified range. There in this formula you can see v dash is the normalized value, then v is the original value which has to be normalized. Then mean a is the minimum value of original range, max a is the max value of original range, and new min a is the minimum value of new range, new max a is the maximum value of new range. So we are using one data where we are supposing the original range to be 10, 20, 10 and 20, and the value v has to be scaled to a new range of 0 to 0 comma 5. So this range we have to scale up in this range 0 and 5. Then here what the min a is the 10 and max a is the 20. The new min a is 0, new max a is 5, and v is equal to 15. So original value that has to be normalized. This we can take in any number within this range, 10 and 20. We're taking v as 15. So the new normalized value will be v dash equal to putting all the values in this formula. Then after all calculation, we will get 2.5. So v equal 15 in the original range, 1020 becomes v dash equal to 2.5 in the new range, 0 comma 5. In this new range, we will get the value. So we just transforming the value so that it becomes easier for us to classify all the values that are coming in this range. Then comes the Z-core standardization. So you can see here, or standard score normalization. So it is used to transform data to have mean of 0 and standard deviation of 1 while comparing data points from different distributions, or when we want to make data suitable for algorithms that assume normal distribution. So here is the formula you can see for Z-score standardization. Here we are just taking another example and putting all those values in that formula. Let's take one example. Uh, we have weights in kg of 5 individuals. So A equals 60, 65, 70, 75, 80. These are the weights of 5 different individuals. Then mean A will be calculated, will get 70. After that, we will calculate the standard deviation A. Before that, we will calculate the variance, which is the square of standard deviation A. Then we are putting all those values we are having in this formula, and we are calculating the variance. After square root, we are getting this 7.07 approx value, and then putting this value in the standardization formula, and then we are getting the final result as 0.71. So what we can say that for standardizing weight of 75 kilo, V equal to 75, then the approximate standard deviation will be 0.71. Like this, we can standardize any value of the data for 60 kilo, 80 kilo, and whatever the data we were having in this data set, so that we can standardize. So these two methods of feature scaling we have seen now. And then moving on to next is discretization. So I've already told you about discretization, that it converts a large number of data values into smaller ones so that the data evaluation and data management becomes easy. Just like normalization and standardization in the previous thing, in discretization also we are just converting a large number of data into smaller values. So here you can see there are different techniques for discretization: histogram analysis, then binning, correlation analysis, cluster analysis, decision tree analysis, and equate with partitioning. So in histogram analysis, upload is used to present the underlying frequency distribution of a set of continuous data. These things we will see later. Just here, just see the definition. With an example, we can get a better idea. Then binning is the data smoothing technique, which helps to group huge number of continuous values into smaller number of bins. So in that histogram analysis of some continuous data are there. Like this, we will get in a curve-like uh, diagram that will show the plotting of the continuous data. And there the huge number of continuous values will be again binned into smaller number of bins. Then correlation analysis. So this is also the technique for discretization where we use it to identify interesting relationships between the data. And then cluster analysis is clustering, where the grouping of similar objects into one group called cluster is done. And then decision tree analysis is done to identify the optimal number of bins. When the model makes a decision tree, then it assigns an observation of each node. Then here you just see one example is given. So here we have age, 10, 11, 13, 14, 17, like this. We have age till 75 before discretization. And then after discretization, we are just dividing the huge data into smaller ones, just as before we have discussed. So age now we are discretizing into young. 10 to 19 will be the age group of young people. Then from age 30 to 42 will be the age group of mature people. And from 70 to 75, the age group will be of old people. Like that, we are discretizing the whole data. And here with the mathematical notation, we are just writing this whole thing as V equal to maximum value minus minimum value by n, where the n is the number of bins or intervals. So in this way, we can discretize our data. Then comes the attribute selection. So attribute or features are the things which we have to identify, and we have to take it from the data itself. Then we can analyze the data and our model can be prepared. The important features of attribute selection is to reduce the cost of learning by reducing the number of attributes and provide better learning performance compared to using full attribute set. So we are taking only the best attributes out of the all. And the two approaches for attribute selection is to filter out the merits of attributes from data, ignoring the learning algorithm. And wrapper approach, the attribute subset selection is done using the learning algorithm as black box. This I will show you. I have written with proper explanation. You can see I will share just now. So here I've written about the attribute selection. It's the process to choose most relevant attributes in a dataset, improving model performance by reducing overfitting, speeding up computation, and enhancing interpretability. So you can see it. Filter approach and wrapper approach. This two-way. We can evaluate in filter approach each attribute independently of any machine learning model. It relies on statistical measures to score and takes features based on their relevance to the target variable. After ranking, only top features are selected. So I've already told you that the most relevant features are selected. And then wrapper approach. So it's learning algorithm treated as black box, means the algorithm is not looked inside thoroughly. Instead, output is seen Finding the feature subsets that maximizes the model performance regardless of model's inner masking. So these two approaches are there where we can use it for attribute selection. Then most filter approach is ranking of attributes according to chi-square values in a two-way table, confusion matrix. This here confusion matrix is made, so you can see. I will share. So here is the confusion matrix. You can see we are just dividing our attributes into different actual class and predicted class, and based upon that, two different classes we have written d0bg and d0bg. So for actual class d0 and predicted class d0, it is coming as true positive. Then actual class d0 and bg predicted class is coming as false negative. Then bg and d0 is coming as false positive, and bg and bg is coming as true negative. These things with uh, an example we will see in later. Just now, see what attribute selection is and how it is done. With a proper example, it will be more clear to you. So here, chi-square test, which is a statistical test that measures the association between two categorical variables, is done. So it is used to measure each attribute, feature, and target variable, class variable dependence between them. If the feature has high chi-square score, then the feature and the target variable are strongly related, and the feature is potentially important for prediction. So this is done also where we have seen in this confusion matrix. So it is done to get the dependency between the attribute and the target variable. And the two-way table here I have already explained you that summarizes the counts of different combinations of categories of two categorical values such as features and class levels. Rows are the actual classes and columns here is the predicted class. Here you can sorry, I will share. I have written this. In the confusion matrix only, I have taken one example. So attribute is color, target class, fruit edible. Then the two values possible is yes or no. Then two-way table combination we can write as red yes, red no, green yes, and green no, where the chi-square can be calculated. If color has high chi-square value, then it is an important part in predicting edibility. This with example will be more clear. Here I have only mentioned about how the two-way table can be prepared based upon the two classes. So with proper uh, learning about a particular example, taking one particular example, you can get the better idea that we will see after in our Python class. Here you can see one example. I have also written this pet preference. So two pets are there, cat and dog. So what will be the preference in urban and rural areas? Urban, the cat preference is 30 and dog preference is 10. The total is 40. In rural, cat preference is 20 and dog preference is 40. So total will come out 60. Then using that formula, whatever it was mentioned in the slide, I'm just showing you again. Here it is the formula we have I've written. You can see how we can write the expected count, how we can calculate it in a two-way table. So x square, larger value of x square will be better attribute. So this is the formula. Using that formula, we'll solve this particular example, what I have shown you about the pet preference. Again, we will move on to our example we're going to solve. So the expected count for urban cats E is E urban, comma cats equal row total for urban into column total for cats divided by total count. We are putting these values from the table. Column total for cats is 40, you can see here. And column total for cats is 50. You can see this total 30 plus 20, 50. And we are putting this here, and the total count is 40 plus 60, 100. We are putting all those values here, and we are finally getting the expected count for urban cats is 20. Then similarly, we can calculate for expected count for urban dogs, rural cats, and urban and the rural dogs using this formula only. From the above table, we are just directly putting the values here, and we are getting the expected count for each. Then we are summarizing the total into table. So these all the values we are putting here and writing the total here 50, 50, 100. Then we are calculating the chi-square statistic x square for urban cats. X square urban cats equal 30 minus 20 to the power whole square divided by 20. We are putting all these values from this table. The formula is this x square equal to summation of observed count minus expected count divided by expected count. So we will be getting this chi-square statistic value, and these are the values we are getting after solving this. And we are just summing all the values of x squared. And finally, we are getting 16.66 values. So this we are getting value, and from the two-way table we can calculate the expected count and the chi-square and we will be finding the value of x square. Whichever the value is higher, then that will be the better attribute we'll consider. Now we will be moving on to next slide. Feature scaling normalization. So it is a technique used to scale data to a standard range or distribution, which is helpful for machine learning and statistical analysis. So here we are just normalizing the data in the data set into a common scale. So here 4 techniques are there for normalization. I will explain it to you one by one. I will first go through the definitions and the formula. First is Z-score normalization. This is the formula you can see where Z equal to standard score, X equal to observed value, mu is mean of the sample, and is the standard deviation of the sample. So all these formulas we can use for normalization, and these are the technique basically. This we will see with an example, some data set I have taken, how we can solve the normalization for this data set. We will see. So this data set you can see I have taken 10, 12, 14, 18, 20. Then we're calculating the mean, and the formula I've already shown you. I've just put this value into that formula and getting the value mean. In the standard deviation calculation, we will first calculate the variance, which will be the square of this standard deviation. And the formula I've already shown you. I'm just putting these values into that formula. And finally, we are getting the value after solving all these things, 10.56. Then for x equal to 10, we are taking our z-score normalization will be, which we will put this value. And we will be getting the value here as minus 1.46 after solving this. So it standardizes the data based on its mean and standard deviation for normal distribution data. Like this, we can check for all the data in the data set, and we will be getting the z-score normalization. Then comes the min-max normalization. So you can see the formula here, x dash equal to x minus mean by max minus mean. So mean is here in this data set is 10, max is 20. Then for x equal to 14, we are calculating min max normalization, which will be x dash equal to putting all these values into this formula, which comes as 0.4. So this scales the data into a range of 0, 1. So it is coming between this range only, 0.4. Like this, we can calculate for each. So this way, it will give our min max normalization. Then again, the decimal scaling normalization we can calculate, which is x dash equal x divided by 10 to the power j. This formula I've already shown you in the slide. So we are considering another data set to visualize this 100, 250, 300. Then here the max is 300. Sorry, this should be 300. So J is 3s, 10 to the power 3 is 1000, which will bring max below 1, adjusting data based on order of magnitude. Then for x equal to 250, we can calculate the decimal scaling normalization. X dash equal to 250 upon 1000. Then we are getting, after solving this, 0.25. So the max will be just below the 1 only. So it is coming under 1 as 0.25. So we are getting this decimal scaling normalization for this value 250. And then we are calculating the standard deviation normalization. So here is the formula you can see. And the data set, previous data set only we are considering here again. We are calculating the mean. You have already seen how to calculate this mean. We are getting the mean as 14.8. Then the number of data points total here, 5 data points are there. We are taking 5. Then for x equal to 12, we are calculating the standard deviation normalization as x dash equal to, we are just putting these values from here into this formula, and solving this we are getting minus 0.56 value. So this enters the data around mean and scales based on number of observation. So this way also we can normalize the data based upon the standard deviation and mean. I will just show you one program to how we can normalize the data using min-max. You can see, I will share it now. Here, using one simple Python code, we are just normalizing the data using min-max. So this mathematical way we have seen, so how through coding we can uh, normalize the data using the min-max normalization. You can see here. In detail, we will learn the Python next few classes. So just for uh, to give you an idea how we can do it, I have just used one simple example. So here you can see the import pandas as PD, import numpy as np, import matplotlib.pyplot as plt, and matplotlib inline. So here we are importing the pandas library, which is used for data manipulation in Python, and numpy library used for numerical operations. So we are importing it. Then matplotlib for creating visualizations is a plotting library we are importing here. In this percentage matplotlib inline here, it is specific to Jupyter notebooks, so which enables the plots created with matplotlib to be displayed directly into the notebook. So this will give you the provision to display it into your notebook. Then we are just taking one data frame, wiki.data frame, income, age, and department. So four values are there, four income values: 15,000, 1,800, 1,20,000, and 10,000. Then age, different ages. 25, 18, 42, and 51. Then department, HR legal, marketing management. We are just creating this data frame to visualize it into a tabular form, just like spreadsheet. And inside this data frame, we are just defining the income, age, and department. And DF will display you the data frame. As you can see here, income, age, and department all are coming into one table. These values you can see. Then moving on to DF scaled equal to DF copy. So here we are creating a copy of the original data frame DF and assigning it to DF scaled. That's why we have written this DF copy. So this will ensure your original data remains unaltered when scaling operations are applied to DF scaled. We are just doing the normalization, min-max normalization. So without altering our original data, we are copying it and then we are normalizing the data. Column names which we are going to normalize is in our income and age. And features equal to DF scale column names will extract the columns income and age from DF scale for scaling and assigning them to features. Then here we are just importing the min-max scaler from scalar.preprocessing, which is a scaling class that normalizes data by rescaling features with a specified range. By default, it is 0, 1. So here we are just scaling the whole data. And DF scaled, we are displaying this, the scaling data without range is, as I have already told you, this we are scaling it into range of 0 to 1. So it is coming like this only, the income and age 0.116 11675 like this. The income is coming and age is coming like this into the range of 0 to 1. So we don't use this data as in this range. And scaling, we will further scaling it into the range of 5 to 10. So that will be more suitable for us to visualize our data. So we are again doing this into the range of 5, 10. And then scaling the columns in features and assigning the scale values back to the corresponding values in DF scale. Then we are uh, transforming this feature values in terms of min and max values of each feature in features, and then transforming these values so they lie between this range. And after finally we are showing this DF scale as this in this form. You can see we are finally getting the normalized form of data from this data. And it is in the range of 5 to 10. So this way, using Python, we can normalize our data using min-max. This is Directly we are importing from the Python packages only, and then we are scaling the data. So the mathematical way I have shown you, and the coding way also I have shown you. So now next we will see the resampling methods. So one example we are considering for toxicity prediction. Toxicity from that you can understand like how we can calculate a particular drug is how much toxic or it's not toxic. So based upon that we are considering a particular drug for uh, giving to humans. So we are just taking one example. This also you will get better idea if we are doing with a particular coding example. So for just to give you a brief idea about the resampling methods, I'm considering this example. So these are the independent variables, the features or descriptors or attributes for the three compounds we have taken. So property 1, property 2, property 3. So these are the different properties of the all the compounds we have used. Just we are just putting some random values here only to give you an idea. So based upon that, whether compound 1 is toxic or not, compound 2 is toxic or not, and compound 3 is toxic or not, we will predict. So this class is the dependent variable. So based upon that only it will come to know. So this is purely dependent on it, and these are the independent variables from the data with which we have collected. From there we are taking the features from the data. So just putting it like this in a way, this also you can get the idea into later examples how we can plot it. For here we have I've written 0 as toxic and X as non-toxic. From here we are just plotting it between P1 and P2. This first compound we are putting it as toxic 1, and P1 and P3 between this we are plotting it as compound 2 is toxic and the compound 3 is non-toxic, like this we are putting. So this what we can say from this, that is it enough to get the to prepare or to predict a model based upon only these three data values? So is it enough? So it will be accurate or not, and only these three features are enough for this model prediction or not? So that we have to consider. So just we will take more compounds. So that will be not enough for any model prediction. So that will be very less amount of uh, data for us to do the prediction. We have to take more data and more features we have to include for the accuracy of the model and training the model. So here the classifier, what I have shown you, so that is a model that categorizes the input data into predefined classes. For example, to classify the emails as spam or not, that can be based on various algorithms such as decision trees, support vector machine, or neural networks, which we will discuss later on. So for that, the classifier, we can build a model. And here, the model hypothesis written for the classifier is the specific formulation or assumption that a classifier makes about relationship between input features and output labels. So the function that a model trying to learn from training data. For example, a linear classifier assumes relationship between input features that can be represented as linear equation. So linear, in this way, uh, it will be look like. Then the decision surface for the classifier is the geometric representation, how a classifier divides the feature space into different regions corresponding to different classes. For example, in 2D space with two features, decision surface might be a line separating points of different classes. Just like a straight line, the decision surface will uh, divide the points of the two classes in 2D space. In just 2D space, it is we are writing in 3D. Just in 2D, it will be like in a straight line, and this will be dividing the two classes and the points of the classes. The decision surface is nonlinear for the decision trees or neural networks, and for linear classifier, it will be linear. So for the performance of the model, so mainly the overfitting, resampling, curves of dimensionality, and dimension reduction have to be taken into account, which I will tell you. So the overfitting is the model when learns training data too well, including noise and outliers. So you have some data, and that from that data, the model is tra- trained, and it has the noise and the outliers within it. It it may have zero error, means the model will perform perfectly on training data, but it will struggles with the new unseen data. So that overfitting uh, uh, account will account for the resampling method. And the resampling is the statistical technique used to evaluate and improve the models by repeatedly drawing samples from the dataset and to assess the reliability and generalizability of the model performance. So we have imbalanced data set where classes occurs in a classification problem are not represented equally, which will pose challenge in training the machine learning models. Suppose we are having 95% of data that belongs to one class and only 5% belongs to another. So it will be an imbalanced data set. And here you can see the imbalanced data set as the sampling, oversampling, and random sampling. So in undersampling, the decrease number of instances in majority class by randomly removing samples to balance the data set. And in oversampling, the increased number of instances in minority class by duplicating existing samples or generating synthetic examples. While in random sampling, it's used to select subset of individuals or observation from larger population in such a way that each member of population has equal chance of being chosen. So from the data set of perspective, these three techniques you can consider. And here I have just shown you one example for toxic and non-toxic prediction. It you can see it represents highly simplified or a realistic model that only prints toxic without actually considering the input data X. Then this model does not make real prediction. Instead, only toxic will be printed regardless of the input. So the 99% accuracy on trained data without doing anything will, the data set is highly imbalanced, as 99% of the data points are toxic. This is also not a good practice, so we have to avoid this. And for this, we have to use the model performance perspective, holdout validation, A4 cross validation, and bootstrapping. So before that, we have to consider about the generalization. That means when the model is able to perform well on new unseen data. And if misclassification in training data is allowed or not forced, then model to classify every single training point perfectly, then the model may generalize better to new data. Also, sometimes uh, some errors are allowed in training data that should be allowed to get a more robust model that captures essential patterns without getting bogging down by noise, improving its performance on unseen data. So this generalization we have to consider for the better performance of the model, and we have to see for the best fitting, where we have to identify that the model that provides closest prediction to actual outcomes in the data set, where by using model selection, where we have to involve different models using cross validation, where the data is split into training and testing sets to evaluate the performance, and we have to use hyperparameter tuning, where we have to adjust the parameters of the models to optimize the performance. Uh, Here I have explained about the generalization. You can see the generalized models have two important aspects to fulfill. So first thing, we have to consider that it must learn decision surfaces correctly with zero error from the training data. Then the model must be able to generalize, that is, deal appropriately with new data. Now, this I have already told you that sometimes allowing some errors in the training data should be allowed to get a more robust model, which will capture the essential patterns. And with zero error also, I told you that it is possible and that we have to train it too much, but it will lead to overfit, and overfitting may fit the training data well, even outliers, but fail to generalize new data, lose performance on new data, while allowing not classify all training data totally accurately, allowing misclassification likely to lead better generalization. And thus non-perfect learning is better in this case. So this best fitting we have to take out from the data points you can see, avoiding this underfitting and the overfitting. So these three methods we are considering what I have told you to get the best fit model. First is the split sample or holdout validation, where we are just dividing the data into training and test and validation set. 60, 20, and 20 we are considering here. But the disadvantage is that it reduces the amount of data available for both training and validation. So it will be reduced as we are already dividing it into three, the original data. So it will reduce the amount of data for the training and validation. Here in this diagram, you can see pass 1, pass 2, pass 3, and pass 4 I have written. So here I have shown you about the k-fold cross validation, which means leave one out. Means the data is divided into k subsets and train k times, each time leaving one subset out for computing the error. First, we are taking this set where it shows the iterations or phases within K4 cross-validation process. So in this data set, we are just splitting into folds. In pass one, fold one will be the validation set. Then we will consider the fold two, fold three, and fold four as training. And then if we are considering pass two, then uh, pass two, fold two will be the validation set, and fold one, three, and four will be the training set, and so on till the pass four. So like this, the K4 cross validation is used, but the main disadvantage is that the network must be retrained many times. So it will be retrained many times uh, in K times, whatever the time you are doing the for K4 cross validation, like 10 or 5, 10, like this times you have to repeat it. Then comes the bootstrapping, where it works on the random subsamples or random shares chosen from the full data set, and the data item of any number is any number of times for validation is selected, and the subsamples are repeatedly analyzed. So this way the bootstrapping is done. These things I have just explained you with the definition. This we will have more idea with one example which we will see in next coming classes. So from this, how long should a model be trained? So before training a model, we have to consider these things. That if the error reaches acceptable level, which is 95%, then we have to stop training that model, and we have to stop if the error fails to improve, or it means it has reached a minimum, and we also have to stop if the rate of improvement drops below a certain level. So basically, we have to establish a balance between no, sorry, not memorization. It will be normalization and generalization, which I have told you. So these things we have to consider. Then after that, we will be coming to the conclusion that the model has been trained perfectly, and can consider that model after training. This with further example will be giving you the better idea how this model classification, validation testing is done. We will see with an example in the next few classes. So till now, any question you have, you can ask. So this terminology may be new to you. So I will share these slides today. You just go through it once, and you can put any question if you have. We will further in the next classes, we will discuss about all this model training validation so that you can get a better idea. For now, any question? And we will wrap up here only. If you find any question, then you can put in the group also. Any question till now? Okay, then if no questions are coming, then we can conclude this class today here. We will continue in the next class, and you can also put if you are having some questions in the group. Okay, then we are concluding here today. Okay, then.